In this video, we're going to review and practice mole conversions and apply those skills to chemical reactions, which is the process known as stoichiometry. Before we can begin working with moles and atoms and etc., we have to really focus on the skill that we need to be successful at stoichiometry, which is using conversion factors. Obviously, in an example like this, it says convert 24 inches to feet. You wouldn't have to really write it out to be able to calculate it. But what I want you to be careful about is that the more you show your work, the more likely you are to notice if you're making a mistake, whether it be multiplication or division. Now, a conversion factor involving inches and feet that you're probably familiar with is that 1 foot is equal to 12 inches. It's not unlikely that you are probably comfortable enough with your conversion factor involving these two units to just know that you have to divide 24 by 12 to get your answer in feet. However, I want you to go through and actually write this out so that you get in the habit of making sure that your units cancel. As the problems get more complicated and involve units that aren't so familiar to you, it's going to be extremely important that you do practice and write these things out so that you can catch your mistakes. So once we've drawn our little boxes here, the first step will be to fill in these little boxes. So I know that in this top left area here goes the number and unit I was given in the problem. So I'm going to write 24 inches up here. Now, you know everything after that is conversion factor. So the only thing that will ever go in this top left spot will be the number and unit you were given in the problem. Everything after that in these spots will be the conversion factors. So your conversion factors are things like 12 inches equals 1 foot, 1 centimeter, or 1 inch is equal to 2.54 centimeters, etc. So the way that you decide how to write the conversion factor is that the equals sign is pretty much like the fraction divider. So one of these is going to be the numerator, one of them is going to be the denominator. The way you select which the denominator will be is by looking to see what unit you need to cancel out. So we don't want our answer in units, or in inches, we want our answer in feet. So we need to cancel out inches. So I'm going to write this conversion factor is that 12 inches is equal to 1 foot. This allows me to cancel out inches when will leave me with an answer with the unit feet. So to solve for this, we would put in our calculators 24 times 1 divided by 12, which we know is 2. And don't forget your units, 2 feet. Let's apply this skill now to conversion factors involving grams and moles that we have done. So you should hopefully recognize that a conversion between grams and moles is a one-step calculation. Now, if we're going from grams to moles, we need a conversion factor that involves both of those units. Hopefully, you can recognize this as the molar mass of neon. So when it asks us to convert 58 grams of neon to moles, we can hopefully recognize that we need to look at the periodic table and at the atomic mass of the element, because the atomic mass is equivalent numerically to the mass of 1 mole of that substance. So if we draw our boxes and we set up the problem, remember the number and unit you're given in the problem is what goes in the top left. So 58 grams of neon. Remember, we don't write anything in here. And we bring down our conversion factor, which is our molar mass. And remember, we got to pick our denominator and numerator. Well, I know that I want my answer in moles, and I want to cancel out grams, so I'm going to write the molar mass so that grams cancels, and we're left with an answer in moles. So right now, you should see 58 grams of neon is going to be multiplied by the molar mass so that grams cancel, and you're left with an answer in moles. So to solve this, we would put it in our calculator as 58 times 1 divided by 20.180, which rounded to sig figs gives you an answer of 2.9 moles of neon. So that example was a problem involving grams and moles. Another conversion that we've already practiced last semester was converting between moles and atoms. When you are going between moles and atoms, which you can tell just by looking at the problem, you must understand that you will never, ever, ever pull a number from the periodic table at this point. So again, if and only if you are converting between moles and atoms, you will never need to look at the molar mass of the element, because that's not coming into play. That only matters when you are trying to deal with or convert to or from grams of a substance. The second conversion factor that won't actually change every time you do the problems is Avogadro's number. Now remember, Avogadro stated that 1 mole of any substance, in this case neon, is equal to 6.02 times 10 to the 23rd atoms of that substance. So let's set up our boxes. Again, we start with the number in unit given, that goes in the top left, so 3.23 moles of neon. And now I want to write my conversion factor, choose my denominator between the two to get moles to cancel. So I'm going to write 1 mole of neon on the bottom and Avogadro's number on the top. Moles of neon will now cancel, and we'll get our answer in atoms of neon. Our answer then, using sig figs, is 1.94 times 10 to the 24th atoms of neon. Both of these, like previous two problems, have been more than review. We have done these calculations last semester, and we revisited these again at the beginning of this unit. The two problems are also one-step conversions, so going between moles and grams or moles and atoms. Now, how does the problem change if we have a two-step conversion? Hopefully you remember that there is no direct conversion between grams of a substance and atoms of the substance. We first have to convert to moles. That being said, our conversion factors, either whether it be grams to atoms or atoms to grams, will always be one step or two steps, the first step being converting to moles. So I'm going to write my given information, 21.5 grams of neon, in the top left. Then I'm going to use my conversion factors to cancel out units. So the first conversion factor I have is that 1 mole of neon is equal to 20.108 grams of neon. Well, I'm going to pick my denominator. I know I need grams to cancel, so I'm going to write 20.180 grams of neon is equal to 1 mole of neon. Then we know that grams of neon will cancel. And right now, if we were to stop the problem, we would have an answer in moles, but we don't want an answer in moles, we want in atoms. So I need to use the second conversion factor, and if I select a denominator, I know I need moles to be canceled out. So 1 mole of neon is equal to Avogadro's number. So once you get it set up, you should see that grams of neon and moles of neon are all able to cancel out, leaving you only with an answer in atoms of neon. So if we plug this into our calculator, we would plug it in as 21.5 times 1 times Avogadro's number divided by 20.108 divided by 1. Which, rounded to sig figs, gives us an answer of 6.41 times 10 to the 23rd atoms of neon. So while this problem was an extra step longer, we didn't actually use any new conversion factors. The past two problems have each been the same thing as this, except now instead of taking each set individually, we just combine the problems. So instead of doing the first problem as just grams to moles and then doing the second problem as moles to atoms, now we've just gone grams to moles to atoms directly without ending the problem. So the question now is, how does any of this actually apply to chemical reactions? Well, as I've said, the past sets of problems involving grams to moles and moles to atoms, etc., have all been review. The one and only conversion factor that is new to you in this unit will be that of mole ratio. And how we understand mole ratio is by looking at the balanced equation. So it's important that if you're doing a problem that involves an equation, that you first make sure it is balanced and that you can clearly read the coefficients, so that you can make sure that you observe the correct mole ratio when doing these problems. So the problem says, given the following balanced equation, how many moles of iron 3 oxide can form from 3.45 moles of iron? So just like all the rest of the problems, I'm going to put the number and unit I was given in the top left box here, 3.45 moles of Fe. Now, we are being asked to convert from moles of iron to moles of iron 3 oxide. So if you look at the balanced equation, where do you find iron by itself? Well, iron by itself is a reactant. Iron 3 oxide, which is what we're trying to convert to, is a product. So now you determine the molar ratio of these by looking at the coefficients. So what the coefficients say is that for every 4 irons that float around with 3 oxygens, you get 2 iron 3 oxides. So the way we use this information in the coefficients is that we now have a conversion factor that says if you've got 4 moles of iron, you'll have the potential to build 2 moles of iron 3 oxide. So now, if you do what we did before and choose a denominator, you're going to pick moles of iron to go in the bottom because you need that to cancel out. So 4 moles of iron is equivalent to 2 moles of iron 3 oxide. Again, this is the only new thing that we've been faced with in this unit. So all I did was put the starting information in the top left box. Then I looked at the coefficients of the balanced equation and wrote my conversion factor so that moles of iron now cancel out. And once I do the multiplication and division, I will be left with an answer in moles of iron 3 oxide. So 3.45 times 2 divided by 4, rounded to sig figs, gives us an answer of 1.73 moles of iron 3 oxide. The next, possibly more complicated example could be one like this problem that says, given the following balanced equation, which is the same as the previous problem, how many moles of iron 3 oxide can form from 62 grams of iron? Now, this is the exact same equation as last time, and I'm asking for the same answer. However, this time instead of starting in moles of iron, I'm starting with grams of iron. So the periodic table square has shown back up on this screen because we're going to need it to convert from grams of iron to moles of iron. So if I start with what I'm given, so 62.0 grams of iron, and I want to convert that to moles. Well, I know by looking at this periodic table square that 1 mole of iron is equal to 55.845 grams of iron. So if I choose a denominator, I'm going to put grams in the bottom so that it cancels out. So I'll have 55.845 grams of iron is in 1 mole of iron. So now grams will cancel out. Right now I'm in moles, but I'm in the moles of the wrong substance. Right now I'm in moles of iron. Well, I want to know how many moles of this guy can I form. So what do we use now? The mole ratio. So if you remember from last time, the way that we calculated or found the mole ratio was by looking at the balanced equation. So for every 4 moles of iron, and again I'm going to put that in the bottom so that moles of iron cancels out, I have the potential to form 2 moles of iron 3 oxide. So now moles of iron will cancel out. And then we can go ahead and do the math problem. 62.0 times 2 divided by 55.845 divided by 4, which rounded to sig figs gives us an answer of 0.555 moles of iron 3 oxide. So far we have done 2 problems involving this reaction. We've done one that was converting moles to moles, and one that converted between grams of one thing to moles of another thing. Well, now let's try to convert from atoms of one substance to moles of another. And you'll notice that the iron square of the periodic table has been replaced by Avogadro's number because we don't have any part of this problem saying anything about grams. So we don't need the periodic table. So if I start with what I'm given, 3.1 times 10 to the 25th atoms of iron, I want to use my conversion factors to be able to get myself to moles of iron. So we remember that 1 mole of any substance, in this case iron, is equal to 6.02 times 10 to the 23rd atoms of that substance. So I'm going to pick a denominator and I'm going to throw 6.02 times 10 to the 23rd so that it can cancel out, so that'll be the denominator, and that's the number of atoms in 1 mole of iron. So now atoms of iron cancel out. I'm in moles of iron, but I want moles of iron 3 oxide. So just like before, we're going to use the mole ratio. And I keep writing it because it's important, and it is the one new conversion factor you have learned in this unit. So we're going to use the mole ratio for every 4 moles of iron. We could form 2 moles of iron 3 oxide. Now, if we plug this into our calculator, you'll see that moles of iron cancels, and it will have 3.1 times 10 to the 25th times 2 divided by Avogadro's number, which make sure if you're not using the EE button that you use parentheses, divided by 4, which rounded to sig figs would give us 26 moles of iron 3 oxide. The next problem we're going to do will involve converting from grams of one substance to grams of another substance. So I've gone ahead and given you the molar mass of iron 3 oxide, which is 159.70 grams per mole. So if we start off with the information that we're given, 21.0 grams of Fe. If we remember back to when we had the periodic table square on the slide, 1 mole of iron was equal to 55.845 grams of iron. And that, again, is just the molar mass of iron. And I've selected to put 55.845 on the bottom so that grams of iron will cancel. Okay, so now I'm in moles of iron. I have to get first to moles of iron 3 oxide, which, what are we going to use? The mole ratio. So looking at our balanced equation, again, we have for every 4 moles of iron that we have, we'll have 2 moles of iron 3 oxide. So that will cancel out moles of iron. Now we need to get to grams of iron 3 oxide. So using the molar mass that I've given you, you're again going to assume that the molar mass of any substance is equal to its atomic weight in grams per mole. So now we need to pick a denominator, which I know that I have moles of iron right here, or iron 3 oxide, so I need moles of iron 3 oxide on the bottom. And remember, anytime you're working with molar mass, it's always the number of grams in 1 mole of any substance. So my numerator will be 159.70 grams of iron 3 oxide. So if we put that in our calculator, 21 times 2 times 159.7 divided by 55.845 divided by 4, we'll see too that moles of iron 3 oxide cancel out, and rounding to sig figs we would get an answer of 30.0 grams, this is why it's important to show your work, grams of iron 3 oxide. The last example I'm going to go over with you is the same number of steps as the previous example. However, we're going to use Avogadro's number again. So this problem says, given the following balanced equation, how many formula units of iron 3 oxide can form from 45.6 grams of iron? Now remember, formula units is along the same lines as atoms and molecules. So 1 mole of anything also applies to Avogadro's number for this. So 6.02 times 10 to the 23rd formula units of anything is equal to 1 mole of that substance. So let's start with what we're given, 45.6 grams of iron. Now we're going to use the molar mass as a conversion factor, and I'm going to select my denominators being the grams so they cancel. That's the number of grams in 1 mole of iron. Now we're in moles of iron right now. Well, we're trying to get to formula units of this bad boy, so we now need to convert to moles of iron 3 oxide. So again, we're going to use the mole ratio. For every 4 moles of iron, we'll have 2 moles of iron 3 oxide. So now moles of iron cancels out, and using Avogadro's number, 1 mole of iron 3 oxide is equal to 6.02 times 10 to the 23rd formula units of iron 3 oxide. Because the conversion factor involving Avogadro's number applies to both or all atoms, molecules, etc., as long as you have 1 mole of the substance. So plugging that into our calculator and rounded to sig figs, our answer would be 2.46 times 10 to the 23rd formula units of iron 3 oxide. Now this last slide here is meant to just kind of show you a simplified version of the big picture. So if you have a balanced equation, so let's just say for this example, A plus B yields C plus D. Now, A and B and C and D can be elements, compounds with pi-atomic ions, etc. It's all sort of the same idea. Don't get bogged down by the complicatedness or the number of atoms on each side. Stoichiometry works no matter how many products and how many reactants there are, or what they involve. Now, if you look at this little map, you can see that based on this balanced equation, you can have a possibility of 3 units of each substance. So if I am talking about substance A, I can either be talking about atoms of A, moles of A, or grams of A. Same with all of the other substances. So there's no direct conversion. If I'm given something of atoms of A, I can't directly tell you how many atoms of B I would have just by doing one step. I would have to follow this map. So to go from atoms of A to atoms of B, I would have to go from atoms of A to moles of A to moles of B up to atoms of B. So this map sort of just gives you a little bit of an idea as to how many steps you might need in your conversions and how many boxes you would have to draw to be able to solve problems. So just like there's no direct conversion between atoms of A and atoms of B, there's no direct conversions between grams of one substance and another substance, or even moles of one substance to atoms or grams of a different substance. So there's no moles of B to grams of C direct calculation. That doesn't happen. So use this, keep this handy so that you can picture or try to understand how many steps and how many conversions to go between units for stoichiometry. Now, the arrows that are blue represent all of the conversions that you're going to do involving numbers from the periodic table, so the molar mass. So the only time you'll ever be using the periodic table for these conversions is when you're going between grams and moles of any substance. Now, the pink arrows represent the conversions involving the mole ratio, which that comes into play with the balanced equation. The orange arrows represent conversions involving Avogadro's number. So there's only 3 types of conversion factors that you really need to be aware of or familiar with. Yes, the numbers will change slightly for things involving molar mass, but and the balanced equations, but all of it will be provided to you. I mean, the molar mass is just given to you on the periodic table. You know Avogadro's number, and you can find the mole ratio just by balancing the equation.